This video we will do potential steps. For potential step, potential energy is equal to 0 for minus infinity to 0, and it is equal to V0 from 0 to infinity. If we draw, this is x and this is V0. From minus infinity to 0, V0 is equal to 0, and from 0 to infinity, V of x is equal to V0. We call this region 1 and we call this region 2. For region 1, we have state function phi1, and for region 2, we have a state function phi2. Energy is equal to kinetic energy plus potential energy. And kinetic energy is equal to P square over 2m plus potential energy. For region 1, energy is equal to P square over 2m. For region 1, potential energy, which is V of x, is 0, and for region 2, so energy is equal to P square over 2m plus, and potential energy, which is V of x, for region 2 is equal to V0. So momentum is equal to square root 2m E minus V of naught, and for region 1, momentum is equal to square root 2m E. We know Schrödinger wave equation is minus h cut over 2m d square phi over dx square plus v of x is equal to iota h cut partial phi over partial t. First of all, we consider a case when energy is greater than V of naught. Classically, the reflective coefficient is equal to 0 and transmitted coefficient is equal to 1. This is classical. Now we will see in quantum mechanics either this relation satisfy or not. We write for region 1, Schrödinger wave equation is equal to minus h cut square over 2m t square phi 1 over dx square, and v of x is equal to 0 for region 1. This is equal to iota h cut partial phi over partial t. And this is also equal to energy E of phi 1. Let 2me over h cut is equal to k1. So this equation becomes minus d square phi 1 over dx square is equal to k1 phi. And the solution of this equation is phi 1 is equal to a exponent iota k1 x plus b exponent minus iota k1 x, which we call equation number 1. for region 2, Schrödinger wave equation is minus h cut square over 2m d square phi 2 over dx square plus, and for region 2 v of x is equal to v naught phi 2 is equal to e phi 2, and this is equal to d square phi 2 over dx square is equal to e minus e naught minus 2m over h cut square phi 2. Now consider let k2 is equal to 2m e minus v naught over h cut square. So this equation becomes d square phi 2 over dx square is equal to minus k square phi 2. Again, the solution of this term is equal to phi 2 is equal to c iota exponent iota k2x plus d exponent minus iota k2x, where a, b, c and d are constants. This term is the plane wave in region 1 in positive direction, which is incident wave. This term is plane wave in region 1 in a negative direction. So it is reflected and phi 2, and for phi 2 d is equal to 0, as there is no reflection in region 2. And this is transmitted wave. So phi incident is equal to a exponent iota k1x. This is equation number 3. Phi transmitted is c exponent iota k2x. This is equation 4. Phi reflected is equal to b exponent minus iota k1x. This is equation 5. Further, we consider flux for incident wave, which is denoted by J minus iota h cut over 2m phi incident star d phi incident over dx minus phi d phi incident star over dx, and phi incident star is equal to a star exponent minus iota k1x. Now put value of phi incident and phi incident star in equation 6. So after solving, J incident is equal to minus iota h cut over 2m, and phi incident is equal to a star iota minus exponent minus iota k1 x, and now we take d phi incident over dx. This is equal to iota a k1 exponent iota k1 x, and d phi incident star over dx is equal to minus iota a k1 exponent minus iota k1 x, and this term is equal to iota a k1 exponent iota k1 x minus, and this term is equal to a star a exponent iota k1 x, and this term is equal to minus iota a star k1 exponent minus iota k1 x. This is equal to h cut over m k1 and a modulus square. Here a star this is also star is equal to a modulus square. Similarly, transmitted flux is equal to h cut k2 over m modulus c modulus square, and flux reflected flux is equal to minus h cut k1 over m b modulus square. We call this equation A, B and C. Now reflection and transmission coefficient is equal to J reflected over J incident modulus, which is equal to J reflection is equal to this one and J incident is equal to this one. So it is equal to modulus of B square over modulus of A square, and transmission coefficient is equal to J transmission over J incident modulus, which is equal to K2 modulus C square over K1 modulus of A square. To find these two values, reflection coefficient and transmission coefficient, we know the value of A, B and C. Now we will use boundary condition. Which is phi 1 at x is equal to 0 is equal to phi 2 at x is equal to 0, and second boundary condition is derivative of phi 1 at x is equal to 0 is equal to derivative of phi 2 at x is equal to 0. phi1 is equal to a exponent iota k1x plus b exponent minus iota k1x, and phi2 is equal to c exponent iota k2x. So first boundary condition give us a plus b is equal to c, which is equation 4, and second boundary condition give us iota k1 a minus iota k1 b is equal to iota k2 c, which is equal to k1 a minus k2 b, k1 b is equal to k2 c, which is equation 5. Now multiply equation 4 by k1. Now this becomes k1a plus k1b is equal to k1c, which is equation 6. Now add equation 5 and equation 6. It gives us 2k1a is equal to k1 plus k2c, and c is equal to 2k1a over k1 plus k2, which is equation 7. Now subtract equation 5 and equation 6. It gives us 2k1b is equal to k1 minus k2c. Now put the value of c from 7 into this equation. This is equal to k1 minus k2 over 2 k1a over k1 plus k2. So b is equal to k1 minus k2a over k1 plus k2. Now put the value of c and b in these two equations. So reflection coefficient is equal to k1 minus k2 over k1 plus k2 whole square, and transmission coefficient is equal to 4 k1 k2 over k1 plus k2 whole square. We further know reflection coefficient plus transmission coefficient is equal to 1. You can prove from these two values. k1 minus k2 over k1 plus k2 whole square plus 4 k1 k2 over k1 plus k2 whole square. This is equal to LCM is equal to k1 plus k2 whole square, and this is equal to k1 square plus k2 square minus 2 k1 k2 plus 4 k1 k2 is equal to k1 plus k2 whole square over k1 plus k2 whole square. This is equal to 1. We know k1 is equal to square root 2m e over h cut, k2 is equal to 2m e minus v naught square root over h cut, and k2 over k1 is equal to 2 square root 2m e minus v naught over 2m a, which is equal to square root 1 minus v naught over a. We can also write reflection coefficient as 1 minus k2 over k1 whole square over 1 plus k2 over k1 whole square. And transmission coefficient can be written as t is equal to 4 k2 over k1 over 1 plus k2 over k1 whole square. Now we will consider a special case when E approximately equal to V naught, then k2 over k1 which is equal to square root 1 minus V naught over E is equal to 0. So reflection coefficient is equal to 1 and transmission coefficient is equal to 0. But classically we have reflection coefficient is equal to 0 and transmission coefficient is equal to 1. So it is deviate. So quantum mechanics result deviate from classical result. Now we consider second case when E is greater than V naught, then V naught over E is approximately equal to 0. So k2 over k1 is equal to 1. In this case, reflection coefficient is equal to 0 and transmission coefficient become 1. So when E greater than V naught, R is equal to 0 and T is equal to 1. It match with classical result. Now we will consider second case when E is less than V naught. Then classically reflection coefficient is equal to 1 and transmission coefficient is equal to 0. We have same potential. V of x is equal to 0 from minus infinity to 0 and V naught when x is equal to 0 to infinity. So for region 1, Schrödinger wave equation remains same and its solution is also remains same, which is equal to A exponent iota k1 x plus B exponent minus iota k1 x, where this term is incident and this term is reflected. But for region 2, wave function phi to change. For region 2, Schrödinger wave equation is minus h cut square over 2m d square phi 2 over d square dx square plus v naught phi 2 is equal to e phi 2 and d square phi 2 over dx square is equal to minus 2m e minus v naught over h cut square, which is equal to 2m v naught minus e over h cut square. And we consider this is equal to k2. So d square phi, this is also equal to phi 2 phi 2 phi 2. D square phi 2 over dx square is equal to k2 phi 2, and this equation has a solution. Phi 2 is equal to c exponent k2 x plus d exponent minus k2 x. When x approach to infinity, exponent k to x also approach to 0. So we take c is equal to 0. So phi 2 is equal to d exponent minus k to x, and this term is equal to transmitted. So phi incident is equal to a exponent iota k1 x, and phi reflected is equal to b exponent minus iota k1 x, and phi transmitted is equal to d exponent minus k2 x. And now we find j, which is flux. J incident is equal to h cut over m modulus a square, and j reflected is equal to minus h cut over m modulus of b, and j transmitted is equal to 0. So reflection coefficient is equal to, which is modulus of j reflection over modulus of j incident. It is equal to modulus of b square over modulus of a square, and reflection and transmission coefficient, which is j transmission modulus over j incident modulus. This is equal to 0. Now we will find the value of a and b. To find the value of a and b, we use boundary condition, which are phi 1 at x is equal to 0 is equal to phi 2 at x is equal to 0, and derivative of phi 1 at x is equal to 0 is equal to derivative of phi 2 at x is equal to 0, and this term gives us a plus b is equal to d, and this term gives us iota k1a minus iota k1b is equal to minus k2 d. Now we will multiply this term by k2. So this is equal to k2a plus k2b is equal to k2d. Now we will add this term and this term. So it gives us iota k1a minus iota k1b is equal to minus k2d. This term is cancelled out. This is equal to iota k1 plus k2a plus k2 minus iota k1b is equal to 0, and b is equal to k2 plus iota k1a over iota k1 minus k2. So reflection coefficient is equal to k2 plus iota k1 modulus square over iota k1 minus k2 modulus square is equal to k2 square plus k1 square over k1 square plus k2 square, which is equal to 1. Now reflection coefficient plus transmission coefficient is equal to 1. So quantum mechanics result match with classical result.